Okay, lesson 3, group activities. If you can't calculate areas from the graph of a derivative like we did in the demo, we can use a graphing calculator to get an approximate value for a definite integral. So we're letting f prime of x be the ln of x. So ln of x is the derivative of some function f. And we're supposing that f of 1 is 4. We want to find f of 2, f of 3, and f of a half. And we'll round to the nearest hundredth because we're going to be using a calculator to estimate some things. So for each calculation, we're going to write down the fundamental theorem with some particular values for a and b. So let's see, I know something about f of 1, and I want to know something about f of 2. So if I calculate the integral from 1 to 2 of ln x dx, where ln x is the derivative f prime, then that should be equal to f of 2 minus f of 1. I know what f of 1 is, it's 4, and I need to find f of 2. So this is going to be minus 4. F of 2 is what I'm looking for. And then this definite integral from 1 to 2 of ln x, that I'm going to get an estimate for on my calculator. So you press math, go to option 9, and we're going to integrate from 1 to 2 of the ln of x dx. So that's 0.386. They told us to round to the nearest hundredth, so I'm going to do 0.39. So 0.39 is equal to f of 2 minus 4. So I add 4 to both sides, and we get that f of 2 is approximately 4.39. Okay, if I want to know f of 3, I could integrate from 1 to 3, because I know something about f of 1. So I'm going to integrate from 1 to 3 of ln x dx, because that's going to be f of 3 minus f of 1. F of 1 is 4. F of 3 I'm going to have to solve for. And the integral from 1 to 3 of ln x dx, I can get an approximation for on my calculator. Hit second enter, and instead of going from 1 to 2, I'm going to go from 1 to 3. And I get 1.30 if I round to the nearest hundredth. 1.30. Solve for f of 3 by adding 4 to both sides, and we get 5.30. Okay, last one, I want to know f of 0.5. So I'm going to integrate from 0.5 to 1, right? I know something about 1, so that has to be one of my bounds. And 0.5 is the one I want to know about. It's smaller than 1, so I'm putting it on the bottom. So I'm going to integrate from 0.5 to 1 of ln x dx, and that should be equal to f of 1 minus f of 0.5. F of 1 I know is 4. F of 0.5 I'm going to be solving for. And that should equal the area underneath ln x from 0.5 to 1, which I can have my calculator estimate for me. So this time my bounds of integration are 0.5 to 1. And I get negative 0.15 to the nearest hundredth. Negative 0.15. So now I need to solve for f of 0.5. And I would add 0.15 to both sides, add f of 0.5 to both sides. So f of 0.5 is approximately 4.15. Okay, so suppose you have velocity and position functions for some particle at time t. Then what is an antiderivative of what? So position is an antiderivative of velocity, because velocity is the derivative of position. All right, now we have some formulas, and we're going to find the general antiderivative of each. So we're looking for a function whose derivative is the function given. So some function whose derivative is cosine x, that would be sine of x. But I can always tack on a plus c, an arbitrary constant, because the derivative of sine x is cosine x, and the derivative of a constant is 0. So the general antiderivative always has the plus c on it. Okay, a function whose derivative is e to the x is e to the x plus c. And a function whose derivative is 4x cubed plus 2x minus 5. We're just undoing the power rule here. So a function whose derivative is 4x cubed would be x to the 4th, because you bring the 4 down and reduce the exponent by 1. A function whose derivative is 2x would be x squared. And a function whose derivative is -5 is -5x, and I still have the plus c. All right, a function whose derivative is 1 over 1 plus x squared. This is one that you, it's rarer, but this is one that you should know. This is arctan. Function whose derivative is 1 over 1 plus x squared is arctan x. Okay, a function whose derivative is the sine of x. Oh, I forgot my plus c in the last one. -1. Okay, k of x is a function whose derivative is sine. So the derivative of cosine is negative sine. So if I start with negative cosine, that would give me a derivative of negative sine. So that would be sine. And then I need the plus c. And then last one, a function whose derivative is x to the 6th minus 1 over x. So L of x, the antiderivative of x to the 6th. So I need to increase the exponent by 1, so I get x to the 7th. But the derivative of x to the 7th is 7x to the 6th. So because there's a 1 in front of this x to the 6th and not a 7, I need to put a 1/7 right here, so that when I bring the 7 down and multiply by 1/7, I get 1. So I have 1/7 x to the 7th minus the antiderivative of 1 over x, function whose derivative is 1 over x. That's one we should know. It is ln of x, and then plus c. All right, so for each of these functions, we want to draw a sketch of an antiderivative on the same axes. And we can mentally smooth out the corners. They're not necessarily sharp corners. Okay, so let's see. This function is a derivative function, and it is entirely above the x-axis. So the derivative is always positive. And when a derivative is positive, that means the function is increasing. Function itself is increasing. And maxes and mins on a derivative correspond to changes in concavity of the original function. So the function is always increasing, and it's got a couple of changes in concavity. And this is going to be, because f prime is decreasing here, that means that f is concave down, then f is concave up, then concave down. So the derivative function is going to, the antiderivative function is going to be always increasing. I can start it anywhere because the plus c means I can shift it up and down. Okay, so this is going to be concave down, then it switches to concave up, and then it's back to concave down, but always increasing. So something like that. Okay, this next one, again, it's always above the x-axis, although I do have this one spot here that's a 0, but it doesn't cross the x-axis. So it's going to have a horizontal tangent line at this place that I just marked, but it's not a max or a min, because it's going to continue increasing after that. So f prime here is decreasing, which means that f is concave down, then f prime is increasing, so f is concave up, and then decreasing, so f is concave down. So it's going to be concave down, up, down, always increasing, and I have a horizontal tangent line at this blue x value. Okay, so it's concave down, Then we have sort of a horizontal tangent line, and then it continues increasing, concave up, and then concave down. Although it looks like right here that is going to cross the x-axis, and the derivative will then become negative, which means that my function f would be decreasing. So it looks like that is actually going to be a max there, like that. Okay, so you can see this should be a horizontal tangent line right there. So you can see that I kind of flattened it out as I drew the change in concavity. Okay, next one. I have my derivative function crossing the x-axis right here, and it's going from positive to negative, which means that my function f is going to go from increasing to decreasing at that spot. So it's going to go from increasing to decreasing. F prime is always decreasing on this first interval, which means it's concave down. So I'm going to have something that looks like that. Okay. So I've got a max here because f went from positive to negative. So f prime went from positive to negative. So f goes from increasing to decreasing, and all of it is concave down. Okay, this spot right here, f prime switches from decreasing to increasing, so it switches from concave down to concave up, but we're still below the x-axis, which means it's still decreasing. So it's still decreasing, but it's concave up. All right, and then this point right here tells me that I have a horizontal tangent line because it's on the x-axis. But I've changed concavity. F prime is going from increasing to decreasing, which means that f switches from concave up to concave down, and I have a horizontal tangent line. So horizontal tangent line, so it looks something like that. Kind of smooth that all out. All right, number 7. My entire graph of f prime is below the x-axis, which means that my entire graph of f is decreasing. Now, the increasing, decreasing behavior of f prime tells me about the concavity of f. So if I start f right here, because it's decreasing, so I'm going to start it up here, plenty of room to draw the graph. Now my first line segment here, f prime is decreasing, which means that f is concave down. So I have to be concave down until about this x value, decreasing, concave down. Then I'm still decreasing because f prime is below the x-axis. F prime is negative, which means f is decreasing, but f prime switches to increasing, which means that f switches to concave up until this x value. So still decreasing, but concave up. And then still decreasing because f prime is still negative, but it switches back to concave down. So something like that. Okay, number 8. I've got a couple of zeros here on f prime. These represent horizontal tangent lines. And the sign of f prime is changing, which means those are maxes or mins. Those are extreme values. Okay, so this first 0 on f prime has f switching from negative to positive, which means that f is switching from decreasing to increasing, which means this is a min. And then my max here, that represents a change in concavity from up to down because f prime went from increasing to decreasing. All right, so up to down. So my min, draw like this, and then I'm increasing afterwards, but at this x value, I'm still increasing because this graph of f prime is still above the x-axis, but it switches to concave down. Okay. And then right here, this x value, f prime switches from positive to negative, from above the x-axis to below the x-axis, which means that f switches from increasing to decreasing. So now we're decreasing. And then this x value changes the concavity. So it's still below the x-axis. We're still decreasing, but it's concave up. And then this x value signifies a horizontal tangent line. And f prime is going from negative to positive. So f is going from decreasing to increasing. So that turns around like that. All right, last one. I have 3 zeros on f prime. Zeros of f prime represent horizontal tangent lines on f, and f prime is changing signs at those zeros, which means that f has extrema there. So here f prime is going from negative to positive, which means f is going from decreasing to increasing. So I'm going to start f decreasing till it hits this x value, and then it's increasing until it hits this x value, and it's going to continue increasing because f prime is still above the x-axis, but it goes from increasing to decreasing, which means the concavity changes. So this is increasing still, but the concavity changes to down. Then this x value, at this x value, f prime changes from positive to negative, which means f changes from increasing to decreasing. So I have a max here. And then at this x value, I have a change in concavity from down to up. So it's still decreasing because f prime is below the x-axis, negative, but now it's concave up until I hit this x value when f prime switches from negative to positive. So f changes from decreasing to increasing.